Honors Chemistry, this is your Day 5 lesson. It's the third lesson of the semester, and it is on measurements. So, significant figures. Significant figures, also known as Sig Fig, indicate the precision of a measurement. That is how closely grouped or how precise, how exactly that you did the measurement. In math terms, they provide a set of rules for how many digits you should use in your answer based on the precision of your laboratory measurements. So let's take a simple example. Let's say you're measuring the dimensions of a room, and there's the room, and there are the dimensions. Length is L is length, and W is width. So you measure the width of the room with a laser device that is precise to 1/10,000th of a meter. The length of the room you measure with an old meter stick, and you measure it much less precisely to just 8.1 meters. To obtain the area, you use the formula area equals width times length. So that would be 8.1 times 5.2143, and you get an answer of 42.23583 square meters. This value indicates a level of precision for the measurement that is misleading, because the length measurement could have actually been anywhere between 8.05 and 8.41 meters with rounding. So if you take 8.1, 8.05, if you had rounded that to one place after the decimal, would have been 8.1, and 8.14, if you had rounded that to one place after the decimal, that would have rounded down to 8.1. So that means your actual measurement could have been anywhere between those two numbers multiplied by 5.2143. So you could have gotten anywhere between 41.975 square meters and 42.444 square meters. That's about a half a meter difference in that range of possible answers. The rules of significant figures limit the number of digits you can use in the answer, and that would be 2. So actually the proper number of figures to represent this answer to is 2 significant figures, 42. You should not put anything after the decimal, and that's as precise as you can show this measurement. So what we're going to learn in this lesson is how did we arrive at that number 42? How did we arrive at 2 significant figures? So here are the rules for significant figures. They're not going to make a lot of sense until you actually work some examples here. So all non-zero digits are significant, no exceptions. Zeros to the left of the leftmost non-zero digit are never significant. Zeros in between non-zero digits are always significant. And zeros to the right of the rightmost non-zero digit are significant if there is a decimal point, and not significant if there is not a decimal point. Some books will say if there's not a decimal point, those zeros to the right are indeterminate. It's uncertain whether they're meant to be significant or not. But just so that we follow the rules strictly, we're going to say if there's no decimal point, then zeros to the right are not going to be significant. So let's look at some examples. 326. See if you can solve these before I reveal the answer. How many significant figures is that? The answer is 3. All non-zero digits are significant. Those are all non-zeros, so they're significant. Go ahead and pause and see if you can do each of these on your own before I reveal the answer. Pause. Okay, and the answer to this is 4 significant figures. A zero between non-zero digits is significant, so all 4 of those digits are significant. 6,020. Pause. And that's 3 significant figures. No decimal, so the trailing zero, the one, that should be the one on the right, the trailing zero on the right, yeah, is not significant, or it is uncertain. We're going to say it's not significant here. Let's try some more. Okay, this one. How many significant figures? The answer is 5. Leading zeros are never significant. Either the 0 to the left of the decimal point or the 2 zeros to the right of the decimal point. They're all to the left of the leftmost non-zero digit, which is at 2. And therefore, none of those zeros are significant. Pause and do this one. And the answer is 1. Trailing zeros are not significant or uncertain if there is no decimal point, and there is no decimal point there. How about this one? 8. All zeros are significant, the one to the right, because there is a decimal point. Again, the comma is, in the United States, a comma is just meant to make the number more readable. It has nothing to do with the actual value of the number or significant figures. That comma means nothing. How about this one? 4. Leading zeros left of the 1 are not significant. Trailing zeros right of the 1 are significant. Multiplication. The numbers being multiplied are called multiplicands, and the answer is called the product. So rules for multiplication. The product should contain the same number of significant figures as the multiplicand with the least significant figures. So let's do some examples here. Okay, so what you're going to see here on the left is the calculator answer. If you multiply 2 times 4, you get 8. So how many significant figures in your final answer of 8? How many should there be? The answer is, that's the significant, well actually it's giving you the actual significant figure. It's 8. 2 and 4 have one significant figure, so the answer can have no more than one significant figure. How about 31 times 23? If you do that on your calculator, you will get 713. What should be your significant figure answer? Think about it, pause, and now we'll continue. 710. Okay, why is that? Each of the multiplicands has 2 significant figures, so the answer is limited to 2 significant figures. So that third digit, the 3, should be rounded, and in this case a 3 would be rounded back down. So it would make the 1, the last significant figure is the 1, it's going to be rounded down back to 1. It's going to stay at 1. But you can't just drop that 0 at the end. I mean, the number is going to be somewhere around 713. You can't just say it's 71. You actually got to put that 0 in there. So the significant figure answer for that is 710. So stop and think about this for a sec if that seemed a little confusing. All right? You have to have the number be around 713. But you can only have 2 significant figures, so that would be the 7 and the 1. Okay, how about this? So first thing is, look at which of the 2 numbers being multiplied has the least number of significant figures. And now you're going to take that answer. That answer has 4 significant figures, so you're going to have to round that to 2 significant figures. So what would that answer be with 2 significant figures? And the answer is 0.34. That second 3, the one on the right, is the rounding digit, and it rounds the 4 back down to a 4, so it stays at a 4. So 0.104 has 3 sig fig, and 3.3 has 2 sig fig, so the answer is limited to 2 sig fig. The answer is rounded down to 0.34. How about this? Think about it. Come up with an answer. 64.1. Each of the multiplicands has 3 sig fig, so the answer is limited to 3 sig fig. The 5 in the final answer rounds the 0 up to a 1. So it's 64.1. How about this one? This one's going to seem strange to you when you see it, but think about it. Just follow the rules. What is a significant figure answer for this? And the answer is 40,000. You can only have 1 significant figure in the answer. The 5 limits the answer to 1 sig fig. The 2 in 42,735 is rounded down to 0, and all remaining digits are 0. So that may seem strange. It may seem like that's very inaccurate. You're just not even close to 4. But remember, the 42,735 is a garbage number. All those extra 4 digits at the end mean nothing because the 5 could have either been 4.5 rounded up to 5 or 5.499 rounded back down to 5. And if you were to multiply those two numbers by 8,547, you'd find a huge range of numbers for possible answers. So the one you have to choose is the one that has the proper number of significant figures. Okay, do a few more. What's this going to be? How many significant figures can it have? The answer to that is 2. So what's the answer going to be? The answer is going to be this, 0.0010. That 4 is just a rounding digit. So it's going to round that 0 back down to 0. And so you see the Sig Fig answer has 2 significant figures in it. The 1 and the trailing 0 are both significant. The zeros to the left are not significant. So 0.10 limits the answer to 2 Sig Fig. The 4 is rounded down to 0. The 1 and trailing 0 are the only Sig Fig. How about this one? Think about it. Okay, and the answer is 42. The measurement example on the earlier slide, that's the one we gave when we were doing the example measurement of the room. The 8.1 limits the answer to 2 Sig Fig. The 2 after the decimal, the second 2, the one after the decimal, is rounded down. So that brings the answer to 42. The rules for addition and subtraction are different than multiplication and division. So the rule for addition and subtraction, you line up the decimals to add and subtract number. The significant figures are determined by the number with the least number of digits after the decimal place. Okay, the only way to understand that is let's just get into an example. But just keep in mind, this is totally different than what you just saw for multiplication. So how many significant figures should this be expressed to? Again, you don't count significant figures here. Here's what you do. You put a line right to the right of the number with the least number of digits after the decimal. That would be the 23.45. It has 2 digits after the decimal, and the 5.736 has 3. By the way, you have to first, of course, when you add decimal numbers, line up the decimal points. So you have to do that first. Okay, so now what do we do? So if you add them, you get this. But the number of significant figures is limited to the number of digits to the left of that red line. That would be the 29.18. That would be it. However, that last 6 is still a rounding digit. Remember, the digit, in all cases, whenever you're doing this, the digit that comes after the last significant figure is the one that's going to be used for rounding. So in this case, the 8 would be rounded up to a 9. So the 6 rounds the 8 up to a 9. The final answer is 29.19. So again, completely different rules for addition and subtraction than there was for multiplication. Okay, how about a combination problem? Let's do a multiplication and an addition. So you use PEMDAS, order of operations, and keep track of the Sig Fig. You do not round until the end of the problem. Practically truncating, that means cutting off after the 4th place after the decimal, is all right. In other words, your calculator might give you an answer that has 7 or 8 digits after the decimal. Do you really have to write all those down when it says not round? No. For all practical purposes, we're not going to be dealing with more than 4 digits after the decimal when it comes down to significant figures. So you can go ahead and just chop off anything that comes more than the 5th, 6th, 7th number after the decimal. You can go ahead and just chop those off. That's what truncate means. Then you assign the correct Sig Fig only at the end of the problem. Okay, so here we have 3.24 times 1.021 plus 12.1. So you have to do both a multiplication Sig Fig and an addition Sig Fig. So first, PEMDAS says that we do the multiplication first. And if you multiply those two numbers, you get 3.30804. Now what you do is you keep track of how many significant figures, but you don't actually cut them off or round them at that point. So that means we're limited to 3 significant figures at this point, and in our final answer at this point, because 3.24 has 3 significant figures. Now we do the second part, the addition. we take that number we came up with, that multiplication, 3.30804, and we add 12.1 to it. When you add, you have to line up the decimals, so we go ahead and do that. And then we place the red line in there. So the red line comes just to the right of the number that has the least number of digits after the decimal. That would be the 12.01. It's going to be 12.1. And so that line goes straight down through the 3.3 number and right past the right side of the 12.1. You add everything up. You still haven't cut off any digits, and you get 15.40804. Okay, so the addition also gives us three significant figures. That one, the 15.4. So both the multiplication and the addition gave us three significant figures. If one of them had been less than the other, that's the one you would use for the final answer. But in this case, both are 3. So both steps 1 and 2 limit the answer to 3 sig fig. So the final answer is 15.4. Okay, let's do another one. This time the only difference is we're putting the addition in front of the multiplication, 6.02 plus 3 times 0.451. Go ahead and pause the video, challenge yourself, see if you can do this, okay? Pause the video now. Okay, so first PEMDAS says we do 3 times 0.451. You do the multiplication first, and what you get is 1.353. However, you're going to have to limit this to one significant figure because the 3 only has one significant figure. But don't round it yet. Don't cut it off yet. Okay, now you're going to go to step 2, and you're going to add that number, 1.353, to the 6.02. Insert the red line right there. Go ahead and add all the digits. And you can come up with, for the addition, 3 significant figures. 7.37, and then the 3 would be a rounding digit. So that would round the 7 back down to 7. So it would be 7.37. The addition produces 3 sig fig, but the multiplication limits the answer to 1 sig fig. So you just have to keep track of your sig figs all the way through these, even though you're not going to actually do the cutting down until the very end of the problem. So that means the final answer is simply 7. It can't have more than one significant figure. 7 is the final answer. So stop and review this problem and be sure you understand how the rules of this problem work. Okay, significant figures with logarithms. We do use logarithms in this class, some, but not a lot. So you'll have to be probably reminded of this rule when we finally do get to them much later in the course. So count the number of sig fig in the number from which the log is being taken. This is called the argument. This is that's just the name of that number, okay? Don't ask why it is, because I don't know. I don't know why they call it the argument. This is the number of digits that should be after the decimal in the log, and that number's called the mantissa. You don't need to know these terms. Okay, example, the log of 12.43. If you did that on your calculator, you'd get that big long number there. Now you see that there's 4 significant figures in 12.43. So what that means is that you should have 4 digits past the decimal point, not 4 significant figures. 4 digits past the decimal point for your final answer. So since the number 12.43 has 4 sig fig, there will be 4 digits after the decimal place in the final answer. So there's the final answer, 1.0945. You'll notice that's 5 significant figures. But that's not the issue. The issue is you want to go 4 places past the decimal point for the sig figs, and that's based on 4 significant figures in the original number 12.43. Okay, just kind of a strange rule, and again, we aren't going to deal with that for a while in this class. Okay, now we're going to get into measurements and how to read measurements, and we will either do some video labs or some online YouTube labs or something to actually do measurements, or we can always hope we'll be back in the classroom to do that, okay? So you've seen a meter stick. This is actually a meter ruler, and I've tried to make it on the screen life size if you have a screen the same size as mine. Anyway, those numbers are the centimeters, those 1, 2, 3, 4 numbers. Those are centimeters. There's 100 of those in a meter. And the little tiny lines on the top, again, we're not concerned with the lines on the bottom. Those are inches, and we don't deal with that in chemistry. But the little tiny lines on the top are millimeters. There's 1,000 of those on a meter stick, and you've all seen a meter stick in the classroom. So the ruler below shows metric units on top, centimeters, and imperial English units on the bottom, inches. Again, we're not going to deal with those. In chemistry, we do all measurements in metric units. The number units on the top, the numbered units on the top are centimeters. The small lines in between each centimeter are millimeters, 1/1000th of a meter. There's 1,000 of them in a meter. There are 100 centimeters and 1,000 millimeters in a meter. Okay, so let's look at some measurements. So millimeters represent a precision of 0.1 centimeters. They're 1/10th of a centimeter. That's what 0.1 means. In addition, the measure is allowed to estimate one more decimal place. Okay, so that's something to realize when you make your measurement. This allows the measurement to be 2 places after the decimal. So think about that for a second. 4 there is the number of centimeters. We can actually read, based on the millimeter lines, one more level of precision. That would be 4.1, 4.2, 4.3, and so forth. That would be one place after the decimal. In addition, let's say you thought the number was somewhere in between 4.1 and 4.2. You can estimate how far in between. I call it the guess digit because you really can't read it. You can just estimate what you think it is. I call that the guess digit. So you can actually estimate to one more decimal place. So you could guess if it was between 4.1 and 4.2. I think it's about 3.3 more. So it's going to be 4.13. So you actually can do 2 places after the decimal. How about this one? So if you look at that, at least where I've tried to draw it as best I could, is 6.7. Right on that 7th mark in between the 6 and the 7. So if I did put it right on the 7th mark, that would be 6.7. But you still get to have a guess digit. One, if you think it's in between those 2 of those tiny lines. Now, if I don't think it is, I think it's right on the 7, then I can call it 6.70. So that one would be 6.70. Okay, C. 10.25. The measure is after the 10 centimeter line and is estimated to be halfway between the 2 and 3 millimeter line after the 10 centimeter line. So you estimate, I think it's halfway between 2 and 3. That means it would be 10.25. Halfway between 2 and 3. That would be halfway between 2 and 3. That would be 0.25. And finally, the last one, let's say you look at that and you say the measure is after the 12 centimeter line and is just before the 4 millimeter line there. Just before you get to 4 millimeters. So you might estimate that's 12.38. Not quite to 4, but just before that. Okay, liquids form what appears a disc on the top, and that is called that's called a graduated cylinder, which you're looking at. We'll learn the name of the equipment at a later time. The disc is called the meniscus. So what you see over there on the right in that brace is called a meniscus. The height of the liquid is measured from the bottom of the meniscus. So you always measure from the bottom. Each of the small lines is a milliliter. So the numbered lines are cubic centimeters. Excuse me, a milliliter is 1 cubic centimeter. So you can either call it a milliliter or a cubic centimeter. All right, a triple beam balance, and you'll use these a lot when we get back into the class. The illustration below shows the beams on a triple beam balance. The center beam is in increments of 100 grams. Okay, so that's the one that's the most, what you would call coarse, C-O-U-R-S-E, coarse weight. It's the one that's the broadest. It's the least precise. In other words, every one of those is 100 grams. And you'll notice there's little notches there. When you use the triple beam balance, you have to be sure that that weight that you can slide across there is actually in one of the notches. It should always be in one of the notches. The top beam is in increments of 10, so that's a little more, that's more precise. That's 10 times more precise than the middle beam. And the bottom beam is in increments of grams. That's the smallest lines are 1/10. The reason they build a triple beam balance this way, where the biggest weight is in the middle, is so that it won't, those beams are not lined up one right on top of the other. They're kind of slightly in front of, the one in the front on the bottom is in front of the one in the middle, which is in front of the one on the top, and they don't want to throw the entire apparatus out of balance by having the heaviest weight up on the top. So they put it in the middle there. Okay, so let's learn how we read this measurement. The reading on the right would be 536.80 grams. The 0 is the estimate digit. The resolution of the image is not clear enough to tell where the point lies between 8 and 9. So first of all, the middle beam tells us we're on 500 grams. We're somewhere on or above 500 grams. The top bar beam tells us that we're at 30. So 500 plus 30, we're at 530. Then the bottom one tells us we're at 6, somewhere between 6 and 7. So we're at 536 point something. And we're going to say that it's at exactly on the 8th little mark between the 6 and the 7. So that would be 536.8. And just like with the ruler, with the meter stick, we get a guess digit in between the two smallest lines, but we can't see that it's, you know, anywhere other than right on the 8, so we're just going to call it 0.80, 536.80. Now, what you would see if you see the triple beam balance up at the top is if this were balancing something at exactly that mass, that little image of the triple beam balance up the top, that bar would be right in the middle. It would be right level, and there are some small lines that you can see. Again, we don't need to go into how to read the balance precisely until we get in the classroom. We'll do that at some time in the future, maybe even on a video. But for right now, it's just understanding how to read the balance, and that's what we're focused on here. Okay, so time is measured in the same units in any system. English system or metric system, it doesn't matter. And you can measure in seconds, minutes, hours, or calendar time. Days, weeks, months, years, centuries, millennium, there's all kinds of ways. It's just anything that we use to measure time. Century, and that's it. Okay, so that takes care of it. So let's review this. What you do is in the lab, there's a certain way that you read your measurement to a certain amount of precision, a certain number of digits based on the instrument that you're reading, whether it's a meter stick or a triple beam balance or a beaker, or it could be a beaker or a cylinder that has liquid in it. So then you read that, you write down that number to the proper number of digits, and then when you go to do calculations, you have to start calculating. Then you use the rules for significant figures to determine what your final calculated answer would be. So measurements first, proper number of digits, and then use the rules of significant figures when you're doing your math in the lab report, proper number of digits, and that gives you the proper number of figures or digits that you should use in a final answer. Okay, so that takes care of this, and we will see you in class.